Hello everyone, this is Celal Güvenç from SOCAR Turkey. Today I will briefly describe the integration, validation, and scale-up for the Nefertiti project demo unit. It's a pleasure for me to contribute to this MOOC and I hope you can benefit from it. I would like to also thank to all the organizers and the project team at the University of Burgos for making this possible. Let's begin with a short introduction and then proceed with the rest of my presentation. I am the Sustainability and Decarbonization Supervisor in SOCAR R&D and Innovation Company. My background is in chemical engineering and my research focused on performance characterization and tracking of photovoltaic modules and designing pilot-scale systems to utilize concentrated solar energy to run high-temperature catalytic reactions. The SOCAR team, including me and some colleagues, is responsible for work package 4 in the Nefertiti project, which mainly includes the integration unit, validation of the demo unit. My team will design, construct, and implement a pilot-scale chemical engineering system to try the hypothesis postulated by Nefertiti projects under real-life conditions. Here's the brief outline of my presentation. I will start by discussing the Nefertiti project and my responsibilities. Then I will mention my approach and continue with the process flowchart. I will touch upon the possible challenges of realizing this experimental setup and finish with the notes and lessons learned. Nefertiti is trying to mimic what plants do to provide food for themselves. The process is called photosynthesis. The plants absorb air and react with water using the energy from sunlight to produce hydrocarbon molecules as big as glucose for their growth. Luckily, scientists have found ways to run this process using special chemicals, and it's also possible to manipulate the outcomes by producing compounds with less carbon and oxygen, such as ethanol, an essential building block and alternative fuel. To do this, Nefertiti requires a two-step photochemical reaction, a system in which we feed carbon dioxide and water to the first reactor. Water gets split into oxygen and hydrogen, and carbon dioxide reduces to carbon monoxide. Oxygen gets separated from the mixture, and hydrogen carbon monoxide becomes a reactant of the second reactor, in which ethanol and water form another catalytic reaction called Fischer-Tropsch synthesis, and they're all powered by sunlight. The membrane system separates water from the remaining reaction mixture, and we end up with ethanol or isopropanol as the final product. The novelty here is the idea to run these back-to-back reactors continuously to make the process more efficient and viable. Responsibility in the project is integrating these two photochemical reactors and some additional units to ensure continuous operation and validate the unit's performance under artificial and natural sunlight conditions. Let's see how a chemical engineer approaches this problem. It's important to remember that engineers are famous for their assumptions. You always get a problem you need to learn more about, and you must assume things to proceed. If you want to avoid assuming too many things, you need to simplify the system so that you know some features. So if I look at the whole Nefertiti unit as a black box, I will see reactants, products, and sunlight going in and out. Then I can label the inputs and outputs and check the mass balance to know the size of my system at the end. I will use this information to specify the size of the equipment. Then I start breaking down the big black box to understand the details of the process. I label flows and process parameters like temperature, pressure, etc. As I shrink the black box, I start specifying the streams that come up, but this comes with a caveat. I have to start making assumptions because I can't know all the flows and other process parameters and why they may change after a chemical reaction. The most significant assumption one usually makes is the chemical conversion of the reactors. You specify that and go on from there, and it affects all other parameters like output temperature, pressure, rate of recycling, etc. Then I specify conversion for the second reactor too. I always remember the range of my assumptions because they are never definite. I will always need to make changes or new calculations based on them, so I always use a safety factor. Depending on the size of your system and the precision required for your task, you can use different margins. After specifying the reaction parameters and making assumptions, I must cross-check to see if my calculations are correct, because no matter how wrongly I assume, the mass balance must be closed due to the first law of thermodynamics. Mass into the system must equal the mass out of the system. This can only change if there's a nuclear reaction, but it is out of scope for now. Having an idea of the range of the system parameters, I think about how to make things work in the physical world, which leads me to equipment selection. We're looking at a preliminary flowchart for the Nefertiti demo unit. It includes the fundamental equipment needed for maintaining flows, temperature, pressure, and the basic energy needs for the reactor. Let's match the sections of the flowchart with the system we will use. The reactants in the system are water and carbon dioxide, and since we have higher than atmospheric pressure and low liquid flow for the water, we choose a high pressure water pump, also known as an HPLC pump. We feed the carbon dioxide from a pressurized gas cylinder. Since we want to mix the reactants well for a proper reaction, we must design a tube with a continuous water flow, where we insert carbon dioxide bubbles inside for maximum mixing performance. In addition, we need a water container that is big enough to provide the necessary amount of water for a reasonable uptime of the whole units. Maintaining the feeding and mixing of the reactants, we can focus on the outlet of the first reactor in the flow sheet. Ideally, we will have a mixture of phases and components at the effluent of the first reactor. In Nefertiti, we aim to separate the oxygen there because we want to feed only carbon monoxide and hydrogen in the second reactor. To do this, we first need to separate phases and components. Therefore, there's a decanter, which separates liquid from gas. We want the excess water and some dissolved constituents separated in the decanter. On top, we aim to have a gas mixture containing hydrogen, carbon monoxide, and oxygen. We will take this and feed it to an oxygen adsorption column, which includes materials that have affinity only for oxygen. Therefore, at the outlet stream of this column, we will get hydrogen and carbon monoxide and send it to the second reactor. From there, the second reaction will occur. We will feed a sample of the effluent stream to analysis devices to understand the amount and content of the constituents. I summarized the essence of the Nefertiti project, the design approach, and the system components. Remember that we must start by making assumptions, considering they are wrong. Therefore, there should always be some flexibility. Occam's razor works mainly. So if you fail with your current design, you can simplify things and do the same job with less resolution. Of course, you should not oversimplify. So there will be cases that seem too complicated to design. You can take steps until you can approach things with reasonable assumptions and combine them, increasing the complexity. Remember that an automated, even a semi-automated, fully operative chemical experimental system is never a one-man's work. Having someone with a background in chemical engineering to select and check the design constraints, someone from mechanical engineering who will help you with the selection, manufacturing, and assembly of the mechanical parts, and someone from electrical, control, and maybe computer engineering background to make the measuring elements communicate each other, the rest of the system, and the human user along with data acquisition and electronically driven actions maybe. It is called the human-machine interface, and those modules help you control and monitor almost everything in your system via a computer interface. While working on many things, having a shared checklist and getting together frequently always help, because a continuous experimental system is like a living organism. Changing one parameter always affects the other parts of the system, so every compartment must be aware of the possible changes. That brings me to the end of my presentation. Thank you for listening to me. Please do not hesitate to write questions or comments in the allocated section.